Let us look how can we calculate acidity. So our goal is to establish pH value of solution of weak acid in water. We will be talking mostly about concentrations about 10 to the negative 3 molar. Why? Because these are concentrations most important for analytical titrations. So our acid HA dissociates into corresponding base and H+. You remember that H+ always sits on solvent molecule. In our case, it sits on water. The main source of proton is HA acid, not H2O. So we can forget about concentration of OH minus ion, which of course is always present. In this case, we can take the expression of acid dissociation constant, which is H plus multiplied by concentration of conjugated base and divided by equilibrium concentration of undissociated acid. Because the only source of H plus is dissociation of HA, the same number of A and H plus are created when HA dissociates, which means number of moles of A and number of moles of H plus are the same, and their molarities therefore are the same. As a result, we can write Ka is H plus multiplied by H plus divided by HA. Next, total concentration of our acid is concentration of undissociated and concentration of dissociated species. Because undissociated species and H plus are the same number, concentration of undissociated is total concentration minus concentration of H plus. So we have such an equation in which we know Ka from reference and we know total concentration. That's how much we put. So we can solve this equation for H plus concentration. How we do that? Bringing this to the left side like this, and then writing it as quadratic equation in standard form. For quadratic equation from algebra textbook, we have a formula in which B is Ka and Kc is our C, and here sign is minus. As a result, we are getting such an expression for H plus. If we know H plus, we can calculate pH by known formula. pH is negative decimal log of concentration of H plus ions. We solve the problem. Now, we can do one more simplification. In our equation, H plus is small number if you compare it to total concentration. Why? Because our acid is weak and it's mostly non-dissociated. In this case, we skip H plus here and we have a simpler equation. H plus multiplied by H plus divided by total concentration equals to Ka. Bringing C here, we have H plus squared is Ka multiplied by C, or taking square root, H plus is Ka by C square root, of course positive square root, because concentration must be positive. The exact equation would be like this. So we can hook our result in this equation and see if it's really much smaller than C. If H plus is much smaller than C, our result will be the same. We can correct it if necessary. Now pH, as usual, is negative log of concentration. Now, if we'll take negative log of this, we can simplify our calculations. Log of square root means we have 1/2 of log. So pH is 1/2 of pKa minus 1/2 of decimal log of C. Remember that P means negative log. So we could write PC, but it's inconvenient. So we have a simplified formula that connects pK and log C. This is perhaps the most convenient form. So let's do a couple of examples. Let's calculate pH of 0.01 100 molar solution of barbituric acid. This is barbituric acid, a very common agent. We use as sleeping pills, and it's kind of basic root molecule of large family of molecules that have enormous importance in physiology. Anyway, let's do calculations. pKa of this compound is known. It's 4.01. 0.01 molar can be written as 10 to the negative 2. So I can write pH 1/2 of pKa, 1/2 of 4 is 2, and 1/2 of log C. So it's 1/2 of minus 2. pH is 1/2 of 4 minus 1/2 of minus 2, and it's 3. Now, of course, I can hook numbers in a larger formula, and using Excel can do all my calculations. In this case, I will receive concentration of 0.00094 and pH will be 3.02. Very close number. Practically, I don't know why you need to do lengthy calculations. Now, let's look at next example. Let's calculate pH of 10 to the negative 5 molar solution of barbituric acid. Simple formula will give me 4.5. But full calculations, like here, will give me 5.04. It's a very significant difference. Now, if we'll consider that our acid is strong for 10 to the negative 5, I can simply say that pH is 5. So my acid behaves like it's a strong acid. Oh, what's going on? Why? Situation is relatively simple. As you recall, that fraction of dissociation changes with concentration. So in our first example, with large calculations, the acid behaves like weak, and with low concentrations, it behaves like strong, almost full dissociation. See, here it's a strong area, here it's a weak area, and here it's something intermediate. If we look at second example, we see the same behavior. Somewhere to 1/2 we have weak acid, and then we have relatively close to strong. So any acid is strong at very low concentration. So which approximation is better, weak or strong? If concentration is larger than K or equal, a weak acid approximation will work. If concentration is much smaller than K, you better use strong acid approximation. Or if negative log of concentration is smaller than pK, it's weak. If negative log is much larger than pK, it's strong. Next example, example 3. Let's calculate pH of 0.01 molar solution of ammonium chloride. Now, ammonium, as we have seen before, is an acid. Why? Because it can donate proton. And it has pKa of 925, so it's fantastically weak acid in water. We can write a quick answer, because concentration is 0.01, so 10 to the negative 2. And we have very simple formula. We hook the numbers, 1/2 of 925 and 1/2 of -2. We have 563 for pH. Full calculations using full formula gives me H plus 2.36 10 to the negative 6, and pH is, well, again 563. This is the same number. Now, what if I'll take a lower concentration of ammonia? For lower concentrations, we are coming too close to 7, to neutral pH. In this case, more complex approach is necessary. There is a simple equation. Instead of square root of KC, I need to take square root of 10 to the negative 14 plus KC. We'll look at this equation later on. But quick number will be pH is approximately 7. What is important? It's important to remember that when you add acid to water, your solution is always more acidic than water itself, and pH is always less than 7. Never write pH above 7 for acidic solutions. If you did calculations and you got such number, stop. You did something wrong. You need to correct this mistake.